Okay, thanks, Aman. Well, this talk is based on some research that I've been working on over the last few years with joint work with Matt James, Valerie Uganovsky, and Naoki Yamamoto. And in particular, this talk is based on a couple of conference papers. One was at the ECC a couple of years ago, talking about what are called phase-insensitive quantum amplifiers. And then just recently, we submitted a paper to this year's CDC on non-reciprocal phase-insensitive quantum amplifiers. And what we're looking at here is trying to apply some ideas from linear systems theory and optimization to this problem, which is a classical problem in quantum information and quantum control, if you like, and seeing if some control theory ideas can lead to some new insights in this area. There we go. So quantum control is part of, I guess, a general area you might call quantum technology and quantum information, which has been an area that's received quite a lot of attention in recent years, in particular in the physics community. But there's a few of us working on these quantum control ideas from a systems theory point of view, and we're hoping that systems theory ideas can add some new insights into these sort of problems. So, for example, quantum computing is an area that has got a lot of attention recently, and in particular, there's a number of technologies that people are looking at in quantum computers. I've got a picture here of a superconducting microwave type quantum computing technology. So that's one of the big areas of advance in quantum computing in recent years. So in particular, companies such as Google, IBM, and Microsoft have made significant investments in quantum computing, trying to develop small-scale quantum computers using these superconducting microwave technologies, such as involving arrays of Josephson junctions, and they're operating at millikelvin temperatures. And they've achieved what they claim are quite strong results so far, even though these are relatively small quantum computers. In fact, Google claimed to have achieved what they called quantum supremacy, in that they said their quantum computer could be used to solve a particular problem that wouldn't be possible to solve with a classical computer. Although the other companies working in this area have sort of disputed this claim and said it wasn't really quantum supremacy. But one thing that I'm interested in, or we've been interested in, is the use of quantum amplifiers, which form an important part of these quantum computing technologies. And in particular, quantum amplifiers are needed to read out the states of the qubits, the bits of the quantum computer. And since they're operating at these millikelvin temperatures, they need to amplify the information and then transfer it back to the classical world at room temperature. Another important area of quantum technology, which has received a lot of interest in recent years, is the general area of quantum sensing, using quantum ideas to sense extremely small quantities. And probably the most important example that people might have heard of in this area is that of the gravity wave detection. So here's a schematic diagram of the LIGO gravity wave detection experiment involving two very powerful lasers and a very powerful laser and an interferometer, which the arms of which are a number of kilometers long. So it's a very big experiment, and that was necessary to detect the extremely faint gravity wave signals. But quantum amplification is also required here in order to aid with the detection of these signals. And so this is an optical technology, and in lots of areas of quantum sensing, optical technologies are also used. So we'll be looking at those two kinds of technologies, mainly the optical technology, but also to some extent the microwave superconducting technology. So I guess the main thing here about quantum physics is that it puts fundamental limits on what you can measure and what you can do in terms of sensing. And in particular, it puts limits on amplification if you want to amplify quantum signals, that in terms of the amount of noise that has to be added in order to achieve a certain level of amplification. So what we're doing is, in fact, looking again at these limits imposed by quantum mechanics from a control systems or linear systems point of view, and giving our interpretation of why those hold, and then using those in the design of optimal quantum amplifiers. So the first case we consider are what's called phase-insensitive quantum amplifiers, which provide amplification while maintaining the coherent structure of the quantum signal. And so that's this phase-insensitive notion. And it turns out that in the physics community, it's been known that this sort of amplification is subject to limits inherent in quantum mechanics that limit the amount of amplification you can get for a given amount of additional noise that your amplifier has to inject into the signal. So then we'll move on to consider a refinement of this problem, a so-called non-reciprocal phase-insensitive amplifier, in which we add an extra constraint which eliminates the back action, if you like, of the signal coming back from the amplifier. And so that's another important factor that in many technologies, such as the microwave superconducting, quantum computing technology, they want to try and eliminate that back action type effect. And so these non-reciprocal amplifiers are a way of doing that. There's other techniques such as using the so-called circulators, but they tend to be very noisy. And if you can do it in a purely sort of linear way, then that's a big advantage. So next thing to look at are the sort of models that we're considering. So in particular, we're considering a class of models called quantum linear systems. And these actually behave in many ways like standard classical linear stochastic systems. And the way these models work is that they use the so-called Heisenberg picture of quantum mechanics. And in the Heisenberg picture of quantum mechanics, the dynamics of the system describe the time evolution of operators on an underlying Hilbert space, so typically an infinite dimensional Hilbert space, and those operators represent physical quantities such as position and momentum. So that's one sort of a main picture of quantum mechanics, but another picture that's also commonly used is the so-called Schrodinger picture, whereas rather than looking at the evolution of these operators, position and momentum, you look at the evolution of the so-called quantum state. So these are sort of dual notions representing the same thing, but it turns out the Heisenberg picture is more convenient for us in that it gives us models that look very familiar from a linear systems point of view. So in particular, these linear quantum system models are described by what we call quantum stochastic differential equations, or QSDEs for short. And what they describe is system dynamics building up from a fundamental building block, which is a quantum harmonic oscillator. So in particular, a typical model would involve a collection of these quantum harmonic oscillators each defined on an infinite dimensional Hilbert space. And then as we're looking at the evolution, the Heisenberg picture of quantum mechanics, we look at the evolution of certain operators. And in particular, for us, it's most convenient to look at the operators known as the annihilation and creation operators. So these are also unbounded linear operators on this infinite dimensional Hilbert space, which in the Heisenberg picture evolve in time. And we describe the dynamics of the system by these QSDEs, which describe the evolution of these operators. So typically we'd have a bunch of these operators, we collect them into vectors. In fact, the adjoint operator of the annihilation operator is the creation operator, and we also group that into a vector of operators. And physically, these operators correspond to the annihilation and creation of a photon within the system. So that's why they're given these names, annihilation and creation operators. And they form a very convenient way to model the sort of quantum systems we're looking at. So being control engineers, we like to use the sort of vector matrix notation. So we define like adjoint operators, transpose of our vector of operators, and also adjoint transpose. Another bit of notation I'll introduce is this so-called doubled up form, that often we're dealing with matrices which have this very particular form. It's like a 2x2 block matrix made up of two matrices, R1 and R2, and then we arrange them in this particular way. And that turns out to be compatible with this idea of modeling the quantum system in terms of these vectors of annihilation and creation operators. Also, this J matrix comes up a lot in the sort of models we're looking at and their properties. Okay, so we're considering these quantum linear systems, and they're modeled by these quantum stochastic differential equations. So a typical equation, set of equations we would look at might look like this. So we're looking at the evolution of these annihilation and creation operators. They're driven by inputs which are typically quantum white noise vectors. So these are quantum versions of the standard Wiener processes. And also we've got the corresponding outputs, which are typically the output field corresponding to these input fields. So if we've got a, say in the optical case, a quantum system such as an optical cavity, then the internal modes of the system would be described by the annihilation and creation operators for that cavity. Acting on that system would be some optical fields, and we can describe those by these quantum stochastic processes, and we'll have an incident field like the input U and a reflected field, which is the output Y. So the main difference between I'll go back to this one, between these QSDs, a model, linear quantum system model like this, and a classical stochastic differential equations, is that these variables, these annihilation and creation operators, are operators, and so they don't in general commute with each other. And so that's kind of a fundamental difference, but otherwise there's a lot of similarities between these systems, because these matrices A, B, C, and D are just, in fact, complex matrices, but they're all finite dimensional. It's only the only infinite dimensional thing here is the underlying Hilbert space, and the fact that these variables are operators on this underlying Hilbert space, so they don't commute with each other. So one important feature of these models is that if you go back to such a QSD model with matrices A, B, C, and D, not every set of such matrices A, B, C, and D would correspond to a real physical quantum system which obeys the laws of quantum mechanics. And it turns out that we can characterize whether a given set of A, B, C, D matrices corresponds to a physical quantum system in terms of this notion of physical realizability. And that means that there actually exists an underlying Hamiltonian, which is an operator describing the evolution of the system, described in terms of a Hamiltonian matrix, and also an underlying coupling operator described by a coupling matrix, which will lead to these QSD equations and the corresponding matrices A, B, C, D. So a set of matrices A, B, C, D in one of these quantum linear system models only corresponds to a real physical system if that is physically realizable, which means that those matrices A, B, C, D can be written in this very particular form in terms of the underlying system Hamiltonian, the underlying coupling operator, and also this underlying scattering matrix. So when we're looking at building quantum amplifiers, we have to restrict attention to quantum systems that are actually physical, that can be actually built. So we restrict attention to these physically realizable quantum systems. And also, corresponding to such a system, we would have the corresponding transfer function matrix, just defined in the usual way. And so we're also concerned with whether a given transfer function matrix is physically realizable, i.e. does it correspond to matrices A, B, C, D, which are of this particular physically realizable form. So a transfer function matrix is physically realizable if it's the transfer function of a physically realizable linear quantum system. Now, it turns out that we can give a very nice characterization about when a given transfer function matrix has this physical realizability property, and it's this frequency domain characterization here. It's actually a JJ unitary property. So the transfer function matrix G is physically realizable if and only if it has this JJ unitary property, and also there's a condition that at infinite frequencies, it just has this form here where S is a unitary matrix. So in designing our quantum amplifier, what we're trying to do is find the transfer function matrix of the amplifier such that this physical realizability condition holds, and then the other conditions we have to satisfy are the gain that we want from the amplifier, and then these additional properties like phase insensitivity or the non-reciprocal property. Okay, and the reason why that is, why we want to be physically realizable, because it's only in that case that the transfer function of the amplifier corresponds to a physical quantum system that could be implemented using physical components, either using quantum optics or quantum superconducting circuits. Okay, so let's move on to the first problem we looked at, this phase insensitive quantum amplifier. And probably it's easiest to talk about this in the optical case to start with. And so for the most part, we'll be talking about the optical implementation of a phase insensitive quantum amplifier. So the first thing to understand when talking about this property, the phase insensitive property, is that in quantum optics, all of the signals we're looking at have two components, or sometimes we call them quadratures. And for example, you can have an annihilation component and a creation component, a position component, or a momentum component, but the quantum quantities always come in pairs. And when we're looking at an amplification, then what we would like is that the relationship between these two pairs, say positional momentum or annihilation creation, is preserved when we do the amplification. So we want, say, both quadratures of the signal to be amplified equally. And this equal amplification of the two quadratures is what in the physics literature they call that phase insensitive. It doesn't change the ratio of the quadratures, and so it sort of preserves the coherent structure of the quantum signal. So in many applications of quantum amplification, that's an important property that you want to have. You want to preserve that coherent property, the ratio between the two quadratures, and so that's a fundamental requirement in any quantum amplifier. And as I said, when people started looking into this maybe 20 or 30 years ago in the physics literature, they realized that there was fundamental limitations implied by quantum mechanics on how much amplification you could achieve in this phase insensitive case in terms of the noise that you had to add. So there's like a lower bound on the amount of noise that needed to be added when you do the amplification. And what we first looked at is rederiving that bound and then coming up with a systematic procedure for designing an amplifier which achieves the bound, which achieves the minimum amount of quantum noise and the required gain, and also a suitable bandwidth. So it turns out the bandwidth is not limited by the quantum mechanics, but would be limited by technological considerations such as how much amplification, if you like, you can get across a range of frequencies within your optical amplifiers. So, but in terms of the theory, it's not really limited. And in our approach, what we did was we started off with designing the amplifier purely at DC to meet all the requirements, and then used an idea based on singular perturbations to then extend the gain of the amplifier out to some required bandwidth. And using, in the optical case, two active devices, which are called squeezers, and two passive devices, which are beam splitters. So it turns out these squeezers are active devices, and the way they achieve amplification is via the use of a nonlinearity, but that nonlinearity is very small, and so we can quite reasonably approximate the nonlinear behavior of these squeezers by a linear behavior, and that's what we'll do in this talk. Okay, so the phase-insensitive quantum amplifier can be thought of as a two-input, two-output, physically realizable linear quantum system, and it's got a transfer function matrix G bar. So the two different types of inputs we've got here, the first channel we've got is the so-called signal input. So this can be thought of as an optical field acting on the system, and then the first channel output is the signal output. So then that optical signal acts on the system, and then we'll have a reflected output, which is S out, and the amplification is from the signal in to the signal out. Now, but as I said, in order to meet the requirements of physical realizability, if we want to get some amplification, we also need, according to the laws of quantum mechanics, to add some noise onto the signal. And so that's what the second channel does. So the second input channel is the noise input, which is unavoidable in quantum mechanics. The second channel output is just the sort of corresponding reflected output of that noise. We don't actually use that, but it's included in there to fit in with our definition of physical realizability. So the other thing to point out is, even though I've written this as a two-channel, two-input, two-output system, in fact, each input and each output has two quadratures. And so in the amplification, as I've said, from the signal in to the signal out, the phase-insensitive property is that we amplify each quadrature the same amount, and so that'll put a constraint on our transfer function, and also the noise will have two quadratures. So in fact, the overall transfer function matrix that we're looking at in this case will be a 4-input, 4-output transfer function matrix. So as I said, that noise output channel is not actually used for anything, but in terms of our definition of physical realizability, we always assume that these quantum linear systems have the same number of inputs and outputs, even if some of those outputs are not used. And as I said, each input and output channel has these two quadratures, and so our overall transfer function matrix is a 4x4 transfer function. And so what we've got to do is design this transfer function, first of all, to make sure that it's physically realizable, and then to give us the right gain and also the physical realizability property. And we want that to happen over a certain frequency range or bandwidth. So writing things out in more detail now, we'll write out the two quadratures of the inputs and output channels. And since we're using this annihilation and creation form, then we've got a primary quadrature, say for the signal out, and then, so that's like the annihilation quadrature, and then the adjoint of that operator becomes the creation quadrature. So, or the creation part of the signal. So we write our 4-input, 4-output transfer function in this particular form. where the quadratures of the signals are split out like that. And that leads to the transfer function matrix having this so-called doubled up form that I mentioned previously. Now, so the problem is to design these two the transfer functions here. These are G and H are both 2x2 transfer functions, and so our problem is to design those two and the elements we've written out like this. So first of all, we have to think of what the constraints are, and the constraints are going to be constraints as a function of frequency. So the first constraint is the phase insensitive constraint, and that comes down to this H11 element. That's that element there being 0, which essentially means there's no crossover between signal in and the adjoint of signal in the amplification process. So that's our phase insensitivity constraint. Then we've got our gain constraint, which is just that we achieve a complex gain of G. For the moment, we'll allow that to be a complex gain at the specified frequency omega. So they're the two constraints we have to satisfy to be a phase insensitive amplifier with gain G. We're assuming that G is greater than 1, so it actually is an amplifier, or the magnitude of G is greater than 1. And for the most part, we'll be concerned purely with this property at DC. And so we'll drop the frequency J omega for the most part and just assume that we're doing everything at DC. So we want our transfer function matrix to be physically realizable, but also we want to minimize the effect of the noise on the output. So if we go back to our diagram here, so the effect of the noise on the output will be the transfer function from the two components of the noise input to the signal output. And so in particular, we're interested in the magnitude of that noise effect. So the quantum noise inputs can be thought of as being standard Gaussian processes like unity variance Gaussian processes. So the quantity that we want to minimize the noise squared amplitude is the amplitude of that overall transfer function, which is given by this quantity here. And as I've said, quantum mechanics tells us there should be a fundamental lower bound on this quantity. And again, we'll just look at that normally at DC. Okay, so now I'll just skip through to our main result in this case. So the main result tells us, first of all, what that lower bound is. And so it says that at any given frequency, that if you want to have a gain G at that frequency, then the minimum amount of noise that you need to put in to the signal is given by, or the noise squared amplitude is given by G squared minus 1. So the gain squared is G squared, and then the minimal amount of noise you have to add onto that is G squared minus 1. So if G is quite large, you have to add almost as much noise as signal. So, and that's kind of the fundamental limitation imposed by quantum mechanics. And so here, this is like the minimum possible noise taken over all possible phase insensitive amplifiers. So all transfer functions satisfying the physical realizability condition, the phase insensitivity condition, and the given gain G. So that's what the minimum is. And our proof of this is really just, first of all, showing that this quantity has to satisfy this bound because of satisfying all these conditions, and then just finding a transfer function which achieves the bound. And it turns out that that transfer function is by no means unique. There's lots of transfer functions that achieves this bound, and this is one particular one that we've looked at. Later on, this was mentioned in the original ECC paper. Later on, we've worked out a characterization of all transfer functions achieving the bound. But for the moment, here we'll just give this particular one. And you can see that that then defines our phase insensitive amplifier at the given frequency, typically DC. Okay, so now we kind of know what the transfer function of our amplifier should be at DC. The next thing is to work out how we could actually build it. We know it's physically realizable, so it should at least be possible to build it. And the way we've proposed to build that is to use a result known as the shale decomposition. And what this result says is, if we're given such a 4x4 matrix, transfer function matrix, say at DC, which satisfies this physical realizability condition. I'll just go back to the physical realizability condition. So it's this here, this essentially G star J, G equals J. So it's a JJ unitary property. Then Shale's decomposition says that you can always decompose this matrix into the product of these three matrices. So S1 and S2 are unitary matrices, and this R and define is a diagonal matrix. So this is kind of defining the active part of the system. And because it's diagonal, what this essentially amounts to is we've got to physically realize these two transfer functions. This G1 corresponding to this R is a 2x2 matrix. So this G1 has got the first component of this R, that's R1, and this G2 is the second component of that R, that's R2. So we've got to realize each of these two transfer function matrices independently, and then we've got this coupling between the two in terms of these two unitary matrices, S1 and S2. Now, it turns out if we're looking at optics, then these unitary transfer function matrices can be physically implemented using beam splitters. And so they're just passive optical devices which couple different light beams together. And in this case, they're just 2x2 matrices. So in fact, each one of these can be implemented by a single beam splitter. And in fact, if you look at the input-output relationship of a single beam splitter, you'll just get a transfer function like this. So it turns out that this every possible unitary 2x2 matrix can be implemented, can be constructed in this way. So the next thing we have to work out is how do we implement these active parts of our amplifier. And the way we're going to do that is that what's called a single channel squeezer. So a squeezer is an optical device which it formally contains a nonlinear optical element, but by suitable linearization, we can come up with a linear model for it, which is very accurate, because in optics, it's very hard to get large nonlinearities. So these nonlinear effects are usually very small, and so linearizations are very accurate. So the sort of linearized model of such a device comes out to be a quantum stochastic differential equation like this. I've only shown the equation for A, the annihilation operator. There's only one mode in this system, so it's only a single quantum harmonic oscillator. It has the annihilation operator and the creation operator, but just by taking the conjugate of this equation, you can get the corresponding equation for the A star, the conjugate, the creation operator. So we've got a couple of parameters here. So this kappa is like the damping in the squeezer. It determines the stability of the system. And then this chi is the nonlinear or active effect. And so the size of chi determines the strength of the nonlinear effect. So putting together this model in our matrix form, we get an equation like this. Now, it turns out that if we don't have enough damping and we have too much nonlinear effect, we could even make this system go unstable. So because it's just a 2x2 system, it's easy to write down the stability condition. is that the damping has got to be greater than 4 times chi-squared, effectively. So in practice, we have to make sure this is satisfied, otherwise we wouldn't have a stable amplifier. Okay, so how such a thing is actually built is something like this. This is a schematic diagram. It's got 2 mirrors, a fully reflective mirror, a partially reflective mirror. The incoming optical signal comes in, some of it's reflected out, some of it goes inside the cavity. We've put this nonlinear material, it's like an optical crystal inside there, which provides the nonlinear effect, and that's what provides the amplification. Formally, there's another mode acting on the system, another optical mode known as the pump mode, which is operating at a different frequency, and that actually provides the energy that provides the amplification, but we just look at the fundamental frequency. Okay, so we want to work out how to design this thing to give us the desired DC gain and also the desired bandwidth. It turns out by using a change of variables, introducing a parameter epsilon, which is going to be like a bandwidth parameter, redefining the variables, we can get a new description of our dynamics here like this. And this kind of looks like a singularly perturbed model, and the smaller we make epsilon, then the larger the bandwidth we can get. Now, for this system, we can work out the DC gain, and it comes out to be a formula like this in terms of this ratio, which is actually the ratio that determines stability. And from that, we can find that, in fact, any of those single channel transfer function matrices that we wanted to get, we could achieve by from such a system. And in particular, from a stable such system, because the alpha parameter is less than 1. And not only that, we can choose this parameter epsilon, at least in theory, to give us any desired bandwidth. So combining all of these results, we get our first main result, which tells us that given any desired gain G for our phase insensitive amplifier, then we can find a corresponding physically realizable linear quantum system which achieves this DC gain and in fact introduces the minimum amount of quantum noise at DC frequency, which is achievable by such a phase insensitive amplifier. And we can also, as we've said, achieve any bandwidth, at least in theory, that we want. And finally, this system can be constructed optically from two beam splitters and 2 of these dynamic squeezes. So let's have a quick example. Suppose we want to achieve a gain of 2, that's 6 dB. We want a bandwidth of 2 × 10⁶ radians per second. And we want to minimize, we want to have the minimal amount of noise necessary. So we plug into our formula and we get the G and H matrices. Then we apply this shale decomposition. We find the corresponding R matrix, the 2 unitary matrices. Then we find the corresponding parameters in our squeezes. We choose the epsilon parameter to get the required bandwidth. And then that defines our complete system. So this is a schematic diagram of what such a system would look like. So as I've said, it involves 2 of these squeezes and 2 beam splitters. We've got the noise input channel, signal input channel, signal output channel, and noise output channel. So that's quite a nice example. We can actually look at the performance of this. The theory just tells us it's going to have the required properties at DC, but once we've designed the complete system, we could look at the properties over a range of frequencies. So we can form the actual transfer function, and then we can look at the 1-1 block corresponding to the signal gain, and the 1,4 block, which looks at which in this case gives us the noise gain. And so if we plot those as a function of frequency, we can see at DC we get the required signal gain, which is 6 dB. The noise magnitude squared is a bit less than that, and that follows pretty close to that out to this required bandwidth of 10 to the 6 radians per second, but after that things roll off. So at infinite frequency we can never get any amplification, so we always have 0 dB amplification, but the amount of added noise actually rolls off at infinite frequency. Okay, so I want to quickly just mention one issue that we've been looking at more recently, which is, can we realize such a phase-insensitive quantum amplifier using microwave circuits? And it turns out that in microwave circuits you can have the equivalent of a optical squeezer. You can have the equivalent of beam splitters, because you can microwaves are in waveguides are very similar to light. So we can do those things, but there's some technological limitations, and in particular for the squeezers, that there's a limitation that the signal coming in is in the same channel, if you like, as the signal going out. So this is a microwave version of a squeezer. It involves one of these Josephson junctions, an inductor and a capacitor connected to a transmission line. But we've only got one transmission line, so the signal comes in and goes out along that one channel. So the optical equivalent to this would be like this. We've got our squeezer as before, but the optical input comes in directly at right angles to the mirror and just goes back out along the same direction. So that puts a limitation on what we can do, and in particular the implementation that we gave before wouldn't really work in this case. So what we could do was something like this, where we use the same beam splitter in both the forward and reverse directions. So the signal can come in, go through the beam splitter, go through the two squeezers, come back out again, and then go back out the same channel. So we could do something like this, and in fact that reduces the number of beam splitters that we need to 1 from 2, because we use the same one twice effectively, one in the forward direction and one in the reverse direction. Now the restriction here is, of course, if we're only using the same one twice, it has to be the same. We can't have 2 different beam splitters. We've got to have 2 identical beam splitters. So the corresponding thing in the microwave case looks like this. We've got our 2 squeezers, a single beam splitter, and so the restriction here is that in the shale decomposition, the 2 orthogonal matrices have to be the same. And the shale decomposition doesn't actually guarantee that. But what we managed to work out was that at least in this case, we could achieve the same noise bound, i.e. g squared minus 1, with a given amplification g, by choosing a different possible transfer function matrix G. Remember, that was non-unique. There was lots of different possibilities. Previously, we just chose one particular one, but another one that also achieves the same bound is this one. Turns out this one is actually a symmetric matrix, and in this case, that was what we need to actually implement our phase-insensitive amplifier in this way. So, as I say, like this, or like that in the microwave. Okay, so that's the phase-insensitive quantum amplifier. We're sort of running a bit short of time, so I won't have a lot of time to talk about the next research we looked at, which was this non-reciprocal phase-insensitive quantum amplifier. So this problem, as I've said, also is a very important problem in many applications, such as quantum computing. And what we want to do is add this additional property that the amplified signal doesn't come back in the same channel as the input signal, but goes through another channel, comes out another channel, and that none of the signal coming in is reflected back. So this situation, it turned out we needed to have 3 channels. We've got a signal input and a signal output here, which are now different. And we want to make sure that none of the signal input gets to the reflected channel from the signal from S out. So the notation that's often used is that inputs and outputs which are on the same level are effectively the input and corresponding reflected output. So we want none of the signal to go from there to there. We want all of the signal to be amplified from there to there. And then we have to add some additional noise as well. And it turns out that we now need 2 channels of noise. Essentially, this noise input is the input corresponding to this output. We need another one as well. You can't do this with just two inputs and 2 outputs. So, but the problem looks very similar, at least conceptually, to the previous one. Now we've got our transfer function matrix as a 6x6 transfer function matrix. We've got some constraints on it, that the phase insensitive constraint, the non-reciprocal constraint, and the gain constraint. So again, we get a setup like this, but now with a bigger matrices, we can write down the blocks of our various matrices that we're trying to design. And we put on the constraints. The phase insensitive constraint now looks like this, and the non-reciprocal constraint is now this one, that none of the signal goes into the reflected channel of that signal. And in this case, we can again write down the noise amplitude squared. It's slightly more complicated now because we've got 2 noise input channels, so we have to take that into account, but it's a similar formula. And our main result is that we can, in fact, achieve this, this structure, this non-reciprocal phase insensitive amplifier structure. And in fact, we get the same noise bounded as before. So adding the extra constraint of non-reciprocal doesn't change the noise bound, surprisingly. So we had more constraints, but it didn't. It turned out it didn't matter. We can still achieve that same property. We've got a more complicated amplifier now because it's a 3 input, 3 output system. But apart from that, the noise bound is the same. Again, to implement this, we can, in optics, we can use the shale decomposition. Now we get 3 squeezes because we've got 3 channels, and we've got a 3x3 unitary matrix for which we need 3 beam splitters to implement a 3x3 unitary matrix. And so our overall optical implementation of the amplifier now might look something like this. So we've got our 3 squeezes, we've got 3 input channels, the signal, the 2 noises, 3 output channels, the signal output. And so this corresponds to the first unitary S1, this corresponds to the second unitary S2. And so we get a very similar conclusion to just in the phase insensitive case, that we can achieve the gain that we want. We can achieve the non-reciprocal property, the phase insensitive property, and the amount of noise we need actually stays the same. And we can achieve any bandwidth we want, at least in theory, but in practice that will be limited by the technology. So to finish up, I should say that we haven't really solved the problem of the non-reciprocal phase insensitive amplifier for the microwave implementation. That's something we're actively working on now. And in that case, we've got these extra restriction, if you like, in the shale decomposition, that the 2 unitary matrices have to be the same. But our conclusions are we've used these ideas from linear systems theory, in particular combining with this physical realizability condition, which enables the linear systems theory to take into account the fundamental limits of quantum mechanics. Turns out that that's this frequency domain JJ unitary condition. We can see how that leads to these fundamental limits on the amount of noise that the amplifier needs to add to the signal. We've worked out how to characterize all of the amplifiers that are optimal in this sense, and how we can implement them in the optical case and in the microwave case, at least in the non-reciprocal, in the phase insensitive amplifier. So in the non-reciprocal case, we've done something very similar. We get a more complicated amplifier, and we've looked at the optical implementation of that, and that's where we're up to. So the other thing, I'll just finish up by saying that there's been a lot of work in the physics literature looking at these problems as well, and in some sense all the conclusions that we came to wouldn't be surprising to someone who's working in this area of physics, that they would say, well, yeah, we kind of knew that. But what we are coming up with is slightly different structures for these amplifiers, but also systematic methods of characterizing all possible amplifiers which are optimal, and systematic ways of designing the optimal amplifiers to meet different constraints. Okay, so I think that's all that I wanted to say. So thanks very much.
Thank you very much, Ian. If there is any question for Ian. Daniel, do you want to ask?
Hi, Ian. For the non-reciprocal case, I don't understand why it's 3 inputs and outputs and not 4. Because don't you need, so you need 1 for each noise, and that's 2. Then you need 1 for the signal output that's being amplified, and then you need 1 for the signal that's being reflected back, so to speak.
Okay, so we've got our signal in, and then we need one noise channel for the where the signal is going to come out, because that's now not going to be the same as where it goes in. But we only need one. It turns out we only need one more to allow for the physical realizability. So the only reason for this third channel is to allow for our transfer function matrix to satisfy the physical realizability condition and meet the requirements of quantum mechanics. So it turns out in the physics literature, we've been looking at the microwave case, and we have found that they do have an implementation which does have 4 channels. So we don't really know in the microwave case, maybe the 4 channels are needed, but at least in the optical case, we've shown that you can get it with only using 3 channels.
But still, so in the first case, there were only 2, right? S
Yeah, in the
and W
phase
and W out.
insensitive. Yeah.
But so W out just corresponded to the noise, right?
In
and
the first
S
case,
out
yeah.
just corresponded to the signal. But in this new case,
Yeah,
S
so
out corresponds to the signal going back out, like the back out through the input. Then you also need 1 for the signal that's actually being amplified. Do you get what I mean?
yeah,
So
yeah,
shouldn't there
that's
be
right.
2 for the signal?
Yeah, so in the first case, the signal that's amplified goes out through the same channel that it comes in effectively. Whereas in the second case, it goes out through a different way. So we have to add 1 more channel.
Oh, so in the second case, it's coming out through W1 out.
Yeah,
Okay.
yeah,
Right.
yeah. So yeah, the notation's a bit confusing, and in fact, we're thinking of changing that because, yeah, that's where the signal comes out, not S out. But
So then what's W1 in for? What goes in there?
it's just noise. So that's, again, that's quantum noise that can't be avoided. So whenever you have a signal coming out in quantum mechanics, you always have to you always have to have something going in. And if it's not a signal, then it's what's called a vacuum noise. So it's just white noise effectively.
So does both W1 in and W2 in come out through W2 out? Does that make sense? Are they added?
Yes,
or?
yeah, they both affect it. So,
Okay.
and that's the noise that you want to minimize. So you can't make that effect 0 because it violates the laws of quantum mechanics, but you can try and design your amplifier to minimize that.
All right, cool. Thank you.
Okay. Thanks, Daniel. Is there any other question? Okay, if there is no other questions, let's thank Ian again and see you everyone next week. Thanks, Ian.
Okay, thank you.